Thank you all. Uh, Now I would like to invite the chief patron of this program and the registrar of Triple IT Naya Raipur, Dr. Chandrasekhar Verma, to deliver the opening remarks. Dr. Verma brings him with vast experience from his time at NSIT Delhi and AICT. Sir, we are truly eager to hear your valuable insights and reflections as we embark on this exciting and enlightening journey together. Over to you, sir.
Thank you, madam. Today's respected chief guest, guest of honor, and other Professor KG sir, who is on the dais, all the faculty members, participants, who is on of the dais. Good morning to all of you. Actually, FDP program is my program. जब मैं AICT में था तो in 2018 it was started. और एफडीपी स्टार्ट करने का मेन जो भूमिका रखा गया था, एक्चुअली बिफोर 2018 इट वाज अ ट्रेंड क्या था कि जितने भी कन्वेंशनल ब्रांच है, मैकेनिकल, सिविल, इलेक्ट्रिकल, इसमें एडमिशन कम होने थे, तो एक कमिटी बैठाया गया. कमिटी ने सजेस्ट किया कि वी हैव टू गो फॉर इमर्जिंग एरियाज इफ यू वांट टू इंक्रीज ग्रास इनरोलमेंट रेशियो, GER. ओके, एंड लेटर ऑन ग्रास इनरोलमेंट रेशियो बढ़ाना भी था, और जो ट्रेंड्स है इमर्जिंग एरियाज के, जो जितने भी ब्रांचेस है, उसको हमारे फैकल्टी को ट्रेंड करना था. दैट्स वाई इट्स नेम वाज अटल ट्रेनिंग एंड लर्निंग एकेडमी इस्टेब्लिश हुआ 2018 में. नाउ इट इज इन अ मेच्योर स्टेट. अब क्या हो रहा है कि हमारे इमर्जिंग एरियाज में बहुत सारे एरियाज भी आ गए हैं, लाइक यूनिवर्सल ह्यूमन वैल्यू. आई थिंक मेनी कॉलेजेस हैज participated or has taken FDP on universal human values, and also Indian knowledge system. तो FDP का मेन पर्पस था क्वालिटी एजुकेशन, सो दैट स्टूडेंट कैन इम्पार्ट क्वालिटी एजुकेशन. In turns, faculty can also develop their biodata resume and also contribute to the society by imparting highly emerging areas technology to the student. Right? अब मेरा स्पीकर्स या इनसे एक अनुरोध है कि जैसा कहते हैं कि कोई भी इमर्जिंग एरियाज हो या कोई भी टेक्नोलॉजी हो, उसका ट्रेनिंग अगर दिया जाए या ट्रेनिंग लिया जाए तो उस लैंग्वेज में होना चाहिए जिस लैंग्वेज में आपको सपने आते हों. जिस लैंग्वेज में आपके सपने आते हैं, अगर उस लैंग्वेज में अगर टेक्निकल एजुकेशन या इमर्जिंग एरियाज का डिलीवरी हो तो वो इनोवेशन में कन्वर्ट हो सकता है. इनोवेशन तभी हो सकता है जब आप इनोवेशन के सारे पॉइंट्स जो है या जो भी करने वाले हो, आप उस लैंग्वेज में करें जिस लैंग्वेज में आपको सपने आते हों। ये तो एक पॉइंट है। सेकंड, इमर्जिंग एरियाज इसलिए भी लाया गया एआईसीटी ने, क्योंकि एक संस्कृत में कहावत है कि योगा कर्मसु कौशलम, यो में कुशलता लाना ही योग है। तो एक ये भी पॉइंट था एआईसीटी के तरफ से कि हम इमर्जिंग एरिया के थ्रू हमारे जितने फैकल्टी मेंबर हैं उसको जितने भी नए ट्रेंड्स के टेक्नोलॉजी है उसको इम्पार्ट करें ताकि उनके कार्यों में कुशलता आए। और मैं उम्मीद करता हूं कि सारे जो पार्टिसिपेंट हैं, हमारे जो स्पीकर्स हैं, चीफ गेस्ट है, वो सब मिलकर अब सबके पार्टिसिपेंट एज वेल एज देम सेल्फ वो अपने कार्यों में कुशलता लाएंगे। यही योग का उद्देश्य है। इसी के साथ मैं अपना वाणी विराम देना चाहता हूँ। थैंक यू वेरी मच।
Thank you, sir. Next, I have the privilege of inviting the Dean Academics of IIIT Nair Raipur, Professor Srinivasa KG, to deliver the welcome address.
So, respected guests on the dais and dear distinguished participants of Atal FDP program on next generation VLSI design. So, I am happy that there is one next generation students also sitting for which the VLSI design is taught. So, and I don't know the demography of the participants कहाँ से आए हैं from different
region
states.
like Andhra Pradesh से आए हैं,
अच्छा,
Chennai
so
से
you
आए
have
हैं,
good, you have a good
Maharashtra
demography
से।
representation, and first of all, welcome you to Triple IT in general and state of Chhattisgarh in Triple IT in particular and state of Chhattisgarh in general. So hope or assume that you have come to a kind of a resort for 5 days. यहाँ का माहौल और even the weather actually suits that kind of atmosphere, and the organizers have planned the contents of the FDP with thorough consultation with the experts from Triple IT as well as outside Triple IT. So definitely you should enjoy this. And because I was also, as Verma sir told, I am also the part of this Atal FDP since the beginning. Actually, this started during the Corona time lockdown period. So I remember when I was there in Triple ITNR. So I conducted around 5 to 6 in 1 year, and later another 5. So later I was also in the consultative committee for scrutinizing the FDP. So there were 2, 3 experts from abroad were consulted, and they changed uh, the way the FDPs are being conducted. I think there is some component on article discussions. So where they emphasize that as a part of this, you should not only listen, you should also read something. And later they also brought in the concept of like advanced, basic and advanced, where some basic concepts and advanced concepts. So every time the AICTE is actually making the training pedagogy different so that people are actually make their mind to really learn the concepts being taught in FDP. So next is with respect to the subject itself, as today we are talking about the VLSI. So the semiconductor manufacturing is actually grooming up. And as you know, this is we are in a generation where this data is growing exponentially in the cycle, positive scale. It is going from hexabytes to megabytes to hexabytes to petabytes to zettabytes to अभी उसका दूसरा nomenclature नहीं आया है. It is growing in that positive scale. On the contrary, the devices are going in the negative scale. So millimeter to centimeter to millimeter to nano. उसके बाद पता नहीं कहाँ आएगा invisible devices. I don't know. People have to dream for it. Whether the science supports that, that is, let us see how it happens. So the devices are going in the negative scale. So now people have to balance these two. So lot of advantages and disadvantages from this kind of exploration, but one has to understand the science behind this. Then only actually what I always say, especially in the semiconductor and anything, think beyond science, what it is. So people have told that you cannot have the speed more than the light. But now people are inventing that, inventing or thinking of inventing devices which can travel beyond the speed of the light. So it is, see, that is what the exploration or the scientific inventions. So it will never stop. It is always a food for thought. So in that direction, the organizers, Dr. Manoj and Dr. Deepika, who themselves are actually doing very good research in this area. They have established state-of-the-art laboratories, and they have obtained funding from various funding agencies to do research in these areas. So definitely they should be able to pull a good resource pool from all over India, and they should be able to give you a good information. Apart from just an FDP, you can continue your friendly collaboration and with IIITNR and with the organizers. You can visit our labs, you can consult our faculty. So this is not, it should not, the relation should not end with only FDP. So nowadays I always tell people cannot actually work in competitive mode. So that is a rat race. You cannot win. Nobody can win. And so people have to work with collaboration and cooperation. So that is always a win-win situation. People have to work with win-win situation. Some of the resources what we don't have, you may have. So actually share the resource, collaborate with the ideas, and explore the unseen world, and perish, sorry, and explore some of, and in the sense that is how actually you can grow in your field. Okay, because the academic world requires collaborative efforts. So in this regard, this FDP should be a starting point, and you can see much better beyond this. So first of all, I thank you all of you for coming all over to ट्रिपल आई टी नया रायपुर. मैं सभी FDP में यही बोलता हूँ, आजकल स्पीकर्स मिलना बहुत आसान है, पार्टिसिपेंट्स मिलना बहुत मुश्किल है. सो आई नो डॉक्टर चंद्रशेखर वर्मा सर विल agree with me. Speakers, participants are really, really very valuable for us. Okay, so sorry, I am not disrespecting. I am also one of the speaker, but I am not telling that. Participants आ गया तो बहुत बड़ा है. So आप आए हो, आप हमारा मेहमान हो. So we are very thankful for coming here, and thank you.
Thank you, sir. We are truly privileged to have with us today as the chief guest for the inaugural session Dr. Y. Malika Arjun Rao, Professor and Head of Departments of Electronics and Communication Engineering at Santhiram College of Engineering. Dr. Rao is a distinguished expert in the field of VLSI design and nanomaterials. We are honored to have with us. Dr. Rao's extensive experience and expertise in these cutting edge areas of technology make him an invaluable resource for all of us. We eagerly look forward to, to his inaugural address, which will undoubtedly set the tone for this program and inspire us all. We are confident that his vision and insights will greatly enrich our understanding and motivate us as we embark on this exciting journey. With great anticipation, I now invite Dr. Y. Malika Arjun Rao to deliver the inaugural address. Sir, over to you.
Thank you very much. Honorable Registrar Sir, Dean, the program coordinators, Dr. Majumdar Sir, and co-coordinator Deepika Gupta, other organizers, and the participants from across the India. Very good morning to all of you. A pleasant morning. I welcome all the participants to this wonderful program. As rightly pointed out by the Dean and Registrar Sir, the FDP is meant for grooming the faculty members so that they'll stay updated with the recent technological advancements in a particular area, and the technology that you experienced or learned here will take it to your classrooms and share with the student community, and which definitely help them to prosper in their academics. In the same way, some of the participants could be from research community, and this FDP will help them in bringing the new explorations in material science and novel designs of memory cells, so that it can be used, these techniques can be adapted to your research or can be extended further. So attending this FTP has multiple benefits, as I said. One is take the contents and give it to the students so that they'll benefit, and you personally benefit, and you can conduct a very good research on that. And that's why the government of India has initiated this and funding the institutions to conduct this FTP. So I hope this FTP will bring you a lot of things, good things to you. I urge all the faculty members to utilize the facility and stay focused during this 1 week long program, which definitely will help you in understanding the technologies, and which can further help you in conducting good research. I congratulate all the organizers, and especially the program coordinator Majumdar sir and Deepika Gupta ma'am for arranging such a wonderful facilities for all of the participants. I hope you have a wonderful stay here, and I wish you a happy learning. Thank you.
Thank you, sir, for your words of wisdom. It is my privilege to introduce our esteemed guest of honor, Dr. Ashish Kumar, Assistant Professor at NIT Raipur. Dr. Kumar holds a PhD degree from MNIT Jaipur, specializing in IC technology and wide bandgap semiconductor based biosensors. His research spans MEMS, NEMS, sensors technology, GAN based HEM devices, biosensors, and thin film technologies. With over 20 publications in reputed journal and conference, Dr. Kumar's work has made significant contribution to healthcare, environmental monitoring, and electronics. I now request Dr. Kumar to address the participants. Sir, over to you.
Yes, good morning to all. So most of the things have been discussed by our chief guest as well our registrar sir and the dean sir. What are the basic things that has to be done here for in this particular FDP? So one thing I think that we can discuss here, that is how to benefit it, because most of the I gone through your program schedule, some hands-on sessions are there. So mostly I request to all the participants, please go through very seriously about the what are the things that will be done through the hands-on, because most of the technical sessions are available in our different sites or different portals are there, but whatever the resources they have for your hands-on session, that are very limited in our India. So basically you should go through them, what are the things that you can observe here, and you can use them for your research. So without taking too much time, again we will discuss in the next session about the what are the new semiconductor devices and what are the semiconductor device fabrication in the next session. So again, I want to congratulate all the participants who have selected for this particular event, and I also want to congratulate to organizer team and Triple IT Naya Raipur for this particular event. Thank you all of you.
Thank you, sir. At this point, it is time to express our heartfelt gratitude to the esteemed dignitaries who have honored with us with their presence. I now request our organizing committee to come forward and felicitate the dignitaries, token of appreciation. I would like to invite Dr. Chandrasekhar Verma to honor Dr. Y. Malika Arjun Rao with a token of appreciation.
आराम से बैठ आराम से
Professor Srinivasa KG to honor Dr. Ashish Kumar with the token of appreciation. Now, I would like to invite Dr. Manoj Kumar Majumdar to honor Dr. Chandrasekhar Verma, sir. Now, I would like to invite Dr. Deepika Gupta to honor Professor Srinivasa KG, sir, with a token of appreciation. As we approach the conclusion of the inaugural ceremony, I would like to invite FDP coordinator Dr. Manoj Kumar Majumdar to extend the vote of thanks. Before we welcome him to the stage, let's take a moment to introduce Dr. Manoj Kumar Majumdar. Dr. Majumdar is an assistant professor in ECE department at IIIT NR. He holds a PhD degree from IIT Roorkee in microelectronics and VLSI. With over 45 years research papers in reputed journal and 60 plus conference publication, his expertise spans in low power VLSI, emerging electronics and nanomaterials. He has co-authored 3 books and contributed to various academic and editorial roles, including serving as a lead guest editor for special issue in VLSI design. Dr. Majumdar is a senior IEEE member, a recipient of multiple awards, and listed in Marquis Who's Who in the World. Thank you. Sir, please.
Thank you, Nidhi, for the brief introduction. So, I would like to first formally thanks to all the participants who have joined us for this FDP program, and kindly have my heartfelt thanks to all of you for coming in these sessions, for attending in this long journey of this basic FDP that has been get by the Atal, AICT Atal program. So, coming to the formally FDP program, I would like to just share some of the brief about this program. So, I hope that all of you have got your registration kit, and if you can find your registration kit, there are some of the evaluation sheets are being provided. So, basically, these evaluation sheets are very important because you need to score at least 70% of the weightage of the total FDP program. Like suppose your attendance should be minimum 80% for this FDP. So we have 10 sessions over there. So you have to attend minimum 8 sessions here. And the weightage for the attendance is the 10% out of that. You have to provide a 3 to 4 page article summary per team or maybe the individual wise, and the weightage will be the 10%. You have to submit a project or the live industry problem solving report. And for that case, the 40% weightage will be there. So that will be based on the lab tutorials or something else. And there will be another report you need to submit on the industrial visit, that is a team wise. So industrial visit has been planned on the 20th of December. So after the industrial visit, you have to submit a report. So and the weightage for the industrial report is the 25%. And another one is the reflection journal that will be also discussed, I think, on the last day, that is on the 21st. So on that basis, the weightage will be 15%. So in this way, the total weightage will be 100%, and you need to score at least 70% on this weightage. And on the last day, there will be one MCQ will be conducted. Okay, so that MCQ will be conducted based on the lectures that has been provided by the different speakers. So that in that MCQ also you have to uh, get at least 75% in that MCQ problems. Okay, and so this is all about this FDP circular. So there are total 10 sessions has been arranged, and out of that, one yoga session has also been there, yoga and the might skill session on, I think, Wednesday. So on that session, you will can relax your mind, and you can also learn how we can relax the mind over there. And there are the other sessions that can be planned based on the technical expertise, and other sessions have been also planned on the lab, in the lab. So basically the lab will be conducted in the VLSI and embedded lab mostly, and some lab will be also conducted on the LPCVD system, that is called the low pressure chemical vapor deposition system, in our incubation center. So I hope that you all will enjoy there and you all will learn. Okay. So now just coming to the formally vote of thanks, I would first like to thank our chief guest, Professor Y. Mallikarjuna Rao from Shantiram Engineering College, for gracing us this occasion. I would like to thank Dr. Ashish Kumar from NIT Raipur. He is a VLSI expert, for gracing us as an expert speaker. I would like to thank our Registrar Sir, Professor Chandrasekhar Verma, our Dean Academics, Professor Srinivasa KG Sir, uh, our Dean R&D, Professor Mithilesh Chobe Sir, he is not here today, and our Senior Professor, Professor Rajeshri Mahapatra Sir. I would like to thank them because of their support and the guidance during the FDP sessions. I would like to thank all the departmental HODs, Professor Maifuz Ali, the EC departmental HOD, Professor Satyanarayan Bhalala, CSC departmental HOD, Professor Santosh Kumar, she is from the DSI HOD, and Professor Ramakrishna Bandi from the Maths department HOD. So their support and their guidance during this FDP has made us really thankful event. And last and not the least, I would like to thank my co-coordinator, Dr. Deepika Gupta. She is really uh, helping me for the in the every aspect of conducting this FDP program. And finally, I would like to thank my research scholars. One is the Mr. Kamal Salanki. I hope all of you know him, correct? And Ms. Nidhi Bhuwal, and Mr. Karthik, and the other research scholars, those who are actually helping me for organizing all this kind of the event. So I hope that all of you will enjoy here. In case of any problem, you can please contact us, and please give your valuable feedback at the end of the FDP program, because your feedback is very important for us for the improving purpose. Thank you so much. Thank you.
Thank you everyone for your time. Now I request you to have high tea at the atrium, and uh, before starting the high tea, we will have a group photo at the outside of this building, and we will gather at 11 o'clock for the first session. 10:40. First session will begin by 10:40. Inauguration now concluded. We are excited to kick off the first session of this faculty development program. Today's session will delve into the future of VLSI design and explore the transformative potential of novel memory elements and nanomaterials. It is my pleasure to introduce today's distinguished speakers, Dr. Ashish Kumar, an assistant professor at NIT Raipur. Dr. Kumar holds a PhD from Malviya National Institute of Technology, Jaipur, specializing in IC technology and wide gap semiconductor biosensors. His research spans several cutting edge fields, including MEMS, NEMS, sensor technology, gallium nitride based HEMT devices, biosensor development, and thin film technology. With over 20 publications in high impact journal and conference indexed in Scopus, IEEE Explorer, and Stringer, Dr. Kumar has made significant contribution to the advancement of sensor technology, biosensors, and semiconductor devices. His research has led to a notable improvement in healthcare, environmental monitoring, and electronics. Today, Dr. Kumar will deliver an expert talk on nanostructured material techniques, characterization, and future prospects, where he will delve into cutting edge techniques for fabricating and characterizing nanomaterials. He will also discuss their potential applications and future direction in various industries. We look forward to gaining valuable insights from Dr. Kumar on the exciting developments in the field of nanotechnology. Sir, over to you.
हो गया क्या बोल रहे हैं क्या है क्या स्लाइड मूवमेंट कैसे हुआ लाइट स्लाइड का सर आप ठीक ठीक है तो कौन सा चल रहा था ठीक है ठीक है ठीक कोई इशू yes good morning to all am I audible yes sir without speaker as well yes welcome to all once again in this session I'm very thankful to Deepika ma'am and organizing team for inviting me for this particular session and I'm also thankful to all the participants who will bear me next 1 hour and 30 minutes. So basically we will discuss the fundamental thing about the nanostructures material and what are the different techniques we are using for that. Is it required? For recording okay that is fine. So I have to be there. Okay. So first I would like to know what is the nanostructures. I think most of the participants are there from the PG and PhD. So I think you are familiar with the nanostructure. What is the nanostructure? Just its names indicate we are including with the nano as well the structure. So what is the range of the nano? This is not the sufficient. So particularly if I'm talking about the dimension of the device, it means it has to be from 1 to 100 nanometer. So whatever the structures you having the particular dimension in 1 to 100 nanometer, all the particular structure will be considered as a nanostructure. It means whatever the material you have studied till now that is relevant to the micrometer, millimeter, and I can say different devices that are existing at present, it has to be different from the nanostructure. So what is the beauty of this nanostructure? It means whatever the properties you was getting for a particular material for a bulk. So best if I'm talking about the bulk, it means I am considering the thickness or I can say the dimension of the material up to micrometer. So it has been observed when if you are going through the same material we are using in the bulk and the same material if you are using for the nano level. So that time it is predicted its property, fundamental property of electrical, thermal and the property that are totally different from the bulk. So now it is a high time to we have to focus on this nanostructures material and also looking for the what are the unique features of these materials at the scale of the nano. Okay, in this particular talk, we will try to give the brief overview regarding that. What are the different techniques we are using for development or for the synthesis of these nanomaterials? Second important part is what are the fabrication techniques we are using for the thin film creation? Because basically you are developing the any material. If you are not working with the any device level, that time it is not useful. So first part is that first we want to analyze the fundamental things, that is synthesis of these material. The second is how to use this material in our device behavior. Okay, and finally we have to ensure whether whatever the material we are using there is it working according to the material properties. So finally we have to characterize them. Okay, and at the we are also looking for some future perspective of that how to use these nanomaterials for our existing devices. So before starting this nanomaterials part, I would like to introduce you some basic research activities that are going with in our group. So first activity that is relevant to that, we are at present we are working on the gain-based technology devices. In these gain-based devices, what are the unique feature of these gain-based devices? Now you are familiar with some electric vehicles. They are using some electric vehicles, but they are limited with the range of the kilometer, how much kilometer they can run by using the existing battery technologies. So similarly, for this particular electric vehicle also we want to some amplifier, we want to some power electronic circuits that has to be worked up to this particular level of the energy required. Like in case of if you are working on the electric vehicles, we are working on the kilowatts, but existing transistors are not able to support them up to this particular range. So now we are looking for any type of the technologies that would be helpful to amplify as an amplifier. So we are looking for some power amplifier that can sustain up to the thousands of volts. Okay. So similarly, in this way also we are looking for some gain-based technology that can be a substitute for the silicon-based technology, and they also offer as a high breakdown voltage, so easily it can be used for the higher power electronics application as well. Now these is some biosensors and some different type of sensor also a fascinating word for us, because everywhere we have to monitor our health, we want to monitor our environmental condition, we are also looking for the so whatever the ingredients you are taking inside, it has to be monitored properly. So in this particular activity, just we have started before 2 years, and that is basically funded by our DST program in the ASEAN India Collaborative Project. So in this particular gain-based technology, we are trying to develop some biosensor that will detect our disease too early, so it can be very useful to detect a particular disease. For example, I am looking for any type of the cancer. I think most of the time you have heard about that. If the cancer patient or disease is detected at the early stage, it can be curable. But if it is detected at the fourth stage, that time we don't have any way to cure it. So finally, most of the time in our rural area, we are getting the detection of this particular disease at the last stage, or sometimes we can say it is a fourth stage. It means now it is a high time we are looking for some devices that has to be used to screening periodically. But problem is that the existing technology, that is the mammography, or you can say this is the X-ray machine, we are preparing for the detection of the cancer. But going through this particular X-ray based technology, again it is harmful to us. Then what are the different ways we can use here for the detection? So now we are looking for some biomarker based technology that has to be considered here. It does not require any type of the invention technology. Only we have to give the saliva, or we can give some urine sample is there, and our sensor will work on that, and finally it will give the result whether you are under the range of this particular cancer or not. So now we are looking for the non-invasive technology as well. It should be rapid and it has to be low cost, because in our India we are working on that. We are the underdeveloping country, so we don't have the too much funds to invest there. So we are looking for the devices that can be used at a low cost and it is easy to accessible. Okay, so this particular device we have designed here. So what is the important thing here? That is, first we have to observe this. Here you can see this stake is there before the source, and then at the below part you can say gallium nitride, aluminum nitride, and sapphire is there. So first we have to optimize it, whatever the resolution we are getting according to the stake only. So first we have to optimize this particular stake. The second part, how to introduce or how you are grafting your sample, that is the saliva or the urine sample in our sensor, because our sensor first has to be detect this particular quantity of the sample, and according to that it has to respond. Is it fine? So now we have just optimized this. Now we are at the stage of we have designed our mask. Now we are looking for the fabrication, because doing the designing or doing the simulation, it is a art, but without any realization or without doing any fabrication of it, we cannot assure that whatever thing we have done really is it feasible or not. So now we are at this stage. Now we are looking for the fabrication process. And in India also, I think you are familiar about the semiconductor mission, because we are very lacking in this particular device fabrication process. So now at present we don't have any technology. Only if I am talking about some limited institute like IIT Bangalore, IIT Bombay, and IIT Delhi, they having the such facility to develop such type of the devices. But problem is that they having the limited access. So we don't have the direct access to them. So we have tried to collaborate with some international, like in Singapore Institute, the A-Star Lab, that is funded by Government of Singapore. So now they are ready to provide this particular step. Only what we have to do, this gallium nitride, aluminum nitride, and sapphire, all things they will do there only. And after that, just I have to do the source, drain, and this metallization I have to do here. So basically, this collaboration of these institutes, we are trying to fabricate it. So these are the results, whatever results we have mentioned there, that are how our sensitivity. Basically, in our biosensor also, I will tell you one more thing. That is, most of the time we are using some DNA or RNA or some protein type of are there. So basically, sometimes they are having some dielectric value that is varying. Sometimes you are finding some charge carriers are there, they are modifying their property. So it means whenever I will introduce our sample in this particular micro cavity is there, here you can see, this is our micro cavity. In this, you are applying your sample is there. So according to this sample, it has to be reflected at this interface. So this interface, it is called the 2DG, two-dimensional gun gauge. It has to be improved. Basically, it is the area where our charge conductors charges are there. It has to be increased or it has to be decreased. Here you can see this is the analysis of that. If you are using the different charge configuration there, according to the positive or negative charge concentration, we are getting the different output characteristics. Okay. So according to that, we have to optimize it. So already we have done that. And the second thing that in this table you can see here, this is the sensitivity analysis with respect to the dielectric. It means all over, if I want to classify our DNA, RNA, or the protein, whatever are available there, it can be classified in two. One is the dielectric base, which doesn't have any charges there, and second is the based on the charges. So based on these two techniques only, we can classify all the biomolecules. So we have tried to optimize all the dimension towards in both dimensions, both particular domains, and we have just analyzed whether if you are changing the charge carrier or whether we are changing some dielectric value, how our response of the device will get modified. This is the one area in which we are working there. The same can be extended towards some metal ion detection in the water bodies also, we can do that. Similarly, some like in the food storage also. In the cold storage, we are using the some particular gas, particular sensor like a methane sensor should be there, for CO2 sensor should be there. So that would monitor the health of our food quality. So similar type of the sensor can be developed through this particular stack only. So it may be extended towards that. The second part, the second domain in which we are working there, that is MEMS based pressure sensor. So basically, this particular work we are doing with the collaboration of CSIR Sri Pilani. So this is the picture here. You can say this is the 4-inch wafer that we have fabricated at the CSIR Sri Pilani only, and this is the same images we have done there. How this micro cavity is as there, and this is our oral device. So basically, is the backside image of this particular device, and this is the front side. And developing this particular sensor is not the sufficient. So again, we have tried to develop some interfacing. So without interfacing, we cannot read what is the response of our sensor. So basically, it is a pressure sensor. It means it has to be measure the pressure. Is there any variation in the pressure? It has to be detected our sensor, and it should be sent in form of the readable form, so user can read. Basically, this similar device is used by the PSLV satellites. While they are launching their satellite, they have to measure the pressure. So according to the pressure, they have to create the body of our satellites. So they are using this particular sensor for this, or you can check with that. So this is the overall device that we have packaged here, and finally this is the interface circuit we are using. So basically, if I want to tell you, in this MEMS based sensor, we have started with the simulation. After that, we have done the fabrication. After that, we have packaged that, and after doing the packaging for the interfacing circuit, we also developed this particular thing. So that is the overall way how to work on any particular device. If you are thinking about any device, so you should always focus on starting from the scrape, that is the simulation, go to the fabrication, package it, and finally it has to be interface with the circuit, and after that you can see it is a sensor is there. Okay. Yes, third work that recently we have introduced here, the fabrication of ZIF, MOF, that is metal organic frameworks are there. Basically, these particular MOF filters are used for the environmental monitoring. Now, I think this is a very big concern for us especially in the winter season. Most of us, we are suffering from the allergy. We are facing this type of situation. It means it is a high time we have to use some filters that has the potential to absorb some PM particles like 2.5 and 5 micrometer or 10 micrometer, so they can observe them, and after that they can save us basically. So this was some proposal we have prepared here, and that was funded by some Rajasthan State Pollution Control Board there. And this particular type of MOF filter we have designed there. So this is our machine. Again, it is an indigenous machine is there. So here you can see, this is our spinster there, that is in which we have loaded our sample. So before we have to processing the ZIF, I have to do some chemical processing. Basically, this is the example of the nanomaterial that we are using there. So first we have to analyze this particular synthesis part, and after that we have to optimize how to create this type of the nanofibers, because creation of this type of the nanofiber, again, it is a critical thing. So first we have to optimize. So what are the important parameters that has to be optimized? Basically, we are using the electrospinning. It means there is one source is collector is there, and there is one source. In between we are applying some electric field. So that electric field will guide our particles. Okay. So these particles has to be collected by our collector, but in a uniform way. So we will get the similar type of the similar type of the fibrous, and these fibrous having the very high surface area, so it has the capability to capture more number of particles. So that is our idea. We want to capture all the PM particles that are available in our ambience. So we have to capture them. So how to ensure that whether we are getting that such type of nanofiber or not? So it means we have to go towards the some characterization facility. So here we are using the scanning electron microscopy to see. Basically, nanoparticles cannot be seen by the naked eyes. So normally we are preferring to use the some electron based microscopy. Even in case of the some micro level, we can use that. We can use the optical microscopes, but optical microscopes also not sufficient for to see these nanomaterials. So to ensure that whether we are getting the some fibrous texture or not, we have gone through the SEM based characterization tool, and here you can say this is the image of the complete sample, and this one is the some, I can say this is the resolved or zoomed picture of that. Okay, so basically these particular tools having the capability to how to analyze that whether you are getting the nanoscale or not, so that can be done through it. So mostly it is observed that in case of the indoors units, they are around 90% PM particles are captured by this particular setup. So we are also trying to hard to get it or it improve its efficiency of that. So now that these were the three areas in which we are working on that, and now we will start the nanostructures. Already we have discussed what is the nanostructure. Yes. So first, already we have discussed how to classify whether the material or whether the if you have any thin film, how to classify whether it is a some nanoparticle or nanomaterial. How to classify that? For example, if you have any thin film, if you have any particles are there, how to determine whether it is a nanoparticle or not? In this range, basically we are looking for the any dimension, like for example, if you are having the thickness, any thin film, it means it has the two dimension as a third dimension, that is the thickness. It should be in this range only, that is range 1 nanometer to 100 nanometer. So whether if you are defining the any material, it is a nanoparticle, so first you should focus on the what is the atomic structure or what is the molecular structure of this particular material, right? So you can compare with that existing some natural example of that, like a width of the human hair is approximately 80,000 nanometer. Okay, so you can compare. We are working with that 1 nanometer to 100 nanometer. Similarly, if I want to classify the some dust particle, again they are having the range of the 60 K nanometer. And the last one, that is the DNA. If I'm talking about the DNA, which having the approximate thickness of 2 to 2.5 nanometer range. So you can visualize that at what level we are working that. Because at the nanoscale, all the property, how these properties are getting modified. Again, I have included one more slide about how to visualize that. These are the natural thing you can compare with them. Like if I'm talking about the arm, which having the 5 mm size. Again, it is a very large if we are comparing with the nanoscale there. Similarly, we can say fly ash also having the 10 to 20 micrometer, human hair already. And if I'm talking about the blood cells, again they are having the 2 to 5 micrometer. So you can visualize that whether we are in which condition we are working or in which type of the particle size we are targeting there. Similarly, now the man-made things are also available. So you can think over about different example of these, like a head of a pin pitch having the 1 mm to 2 mm. But whatever the MEMS devices already we have discussed, again they are having the dimension of the 10 to 100 micrometer. So I think now you are able to now to understand what is the particular dia or particular dimension in which we want to work. So any example that you can give, or you have heard about the nanoscale? Any example? Carbon nanotubes, that are the example of this nanomaterials also. And one more example, that is the carbon buckyballs. It is having the 1 nanometer diameter. So basically, based on the different technology or different technological nomenclature that you have heard here, have you heard about like a newly named that is quantum dots? Have you heard about the quantum dots? So these quantum dots having the dia of the 1 to 10 nanometer only, and most of the material that are made from the either it is a metal, semiconductor, and some magnetic material having the property of in this particular range. Some other materials also some ceramic oxide like silicon dioxide and zinc oxide having the dimension of 1 to 100 nanometer dia. Similarly, if I'm talking about some nanowires, again recently it is introduced new term that is the nanowires. Have you heard about anything about the nanowires? Where we are using them? You are right. Basically, whatever the things we are doing, like if you have heard about some piezoelectric materials that are cell power generating. So mostly we are targeting the any structure that can be done in a form of the wires. Some nanotubes, again it is a carbon based, most of the time carbon based tubes are there. These are having the range of 1 to 100 nanometer. And the nanoporous solids that is having the dia of 0.5 to 10. Okay, so that is the zeolite. That is the example that is ZIF. Earlier we have discussed in the pollution part. That is the part of the nanoporous solids. And similarly, we having the 2D and 3D dimensions, which having the dimension in this particular range. So if I want to summarize what is the nanostructures materials, it means first we have to focus on that. What is the size of the atomic? What is the size of if it having any molecules? So it should be fixed per. Okay. So according to that, we have to target the application area. So if you are looking for the any application, if you are looking for the any synthesis of the material, that is the different thing, because synthesis part is totally different. Or if you are using that particular material in application area, that time it is different, because in the synthesis part what we are doing, just we are analyzing that what is the material, what are the different phases of that, what is the crystal structure of that. Is it fine? But in case of the application, it means we are looking for the targeting like if you are using some zinc oxide layer, it means before that we having that some thickness of that, and after that also we having some layer. It means both the layers should be compatible with the particular layer. Is it fine? Okay, so first we have to check the compatibility of these nanomaterials with the existing device. If it is compatible with that, so after then we have to think over whether it is feasible to do the fabrication of that, because most of the time we are working on the transistor. In the transistor, do you know all the fundamental things are fixed, because most of the time we are working on the silicon only. So if you are introducing the any type of the nanoparticles, so first we have to check whether our fabrication technique is completely compatible with that our most technology. So first it has to be fixed. But now these days we are getting the such type of the facilities or such type of the techniques that can be ensured before the doing the any fabrication. And what is this particular techniques? That is the simulation. So most of the simulation tools having these particular nanomaterials, you can introduce similar type of the layer in our device. You can check whether it will work fine or not. So before going the any fabrication process, we have to ensure through the simulation as well. Now these days some analytical techniques are also available. It has to be checked before that. So once you are sure about that, whether our material is compatible with the CMOS technology, so then you can use this particular material for our device level. So what are the important things that have to be undertaken here for the fabrication? If I'm talking about the thickness, first I have to ensure that what is the size or what is the dia of our material, because only at the nanoscale I will get the different property that already we have analyzed them. Okay, and what is the second thing? How these items or these nanoparticles are get arranged in a particular device. First thing, we have to ensure that size of our nanoparticles. Second thing, how they are arranging themselves. If they are arranging the particles in the nano tube form, nano virus form. So according to that, you will get the response of the device. Fine. So we have to check the size, shape, and the morphology of the devices. It means in our hand we have the capability to analyze these particular materials in form of the thin film before introducing the device fabrication. Okay. Initially, we have done the synthesize the material. After that, we have to work on that, optimize the particular recipe, or I can say particular morphology and alignment of the all the nanoparticles on a thin film. And once you are sure about the creation of this particular thin film, then you can move towards the device application. So these are the some again classical examples are there. All the dimension having the 100 nanometer. So you can say nanopart that are called the nanoparticle quantum dots. And similarly, some nano rings also we are introducing in the some devices to improve their performance. If the any dimension having the 2-dimension less than nanometer, it means these are called the nanotubes. Last example that we have discussed, nanofibers and some nanowires. You can say this is the classical pictorial representation of that. In the length only we having the more than 100 nanometer. Dia, all things are in this category only. And next example, that is 1 dimension is the less nanometer. So these are called the thin films and layer and coatings are. It means according to that, I think if you are going through the some recent literature, you find it like a 0-dimensional, 1-dimensional, 2-dimensional, 3-dimensional. So mostly if you heard about the some graphene all type of devices, these are comes in the category of a 2-dimension, not a 1-dimension. It means if I'm talking about the 2-dimension, 2-axis, no, 2-dimension, it means 3rd dimension is under the control. So always if you are going through the any literature, you find like we are using the graphene layer as possible as thinnest. So normally if it is possible, we are looking for the 1 layer, 2 layer, 3 layers. So if you are using the, like for example, I am using the graphene in any electronics device, and if you are using the 5 layer of the graphene, that time response would be different. If you are using the 2, the difference totally response would be different. And if you are looking for the 1 layer of, that time you will get that what is the beauty of the graphene that we are using. But problem is that we are working on the nanoscale. So that time doing the fabrication at the level of the single layer, it is very tough. Okay, just we have tried one more example of that, how to do the fabrication of that, because at that present time, if I'm using the graphene, you can use the in the raw materials, they are using in the different type of the sensors, they are using in different type of the transistor as well, because that graphene having the high conductivity. So if you are replacing your source to drain channel conductivity through that, so it is giving that tremendous response. So now it is a graphene having a very lot of applications are there. So again, if you are thinking about the use of this particular graphene in your any device or any research, always think about that how to do the fabrication. Because doing the simulation, that is fine. You can publish the papers as well. But really, if you want to contribute something towards your society, so that is really whatever you are doing, it is able to produce some output there. So I think this particular talk will help you to whenever you are thinking about any material, always you should think about that whether it is feasible. Do you have any type of the facilities at your end? These type of facilities are available at the external or I can say out of your institute. Always think about that. Because the novel or innovation idea only can comes from your creative mind only. There is no need to go through a lot of literature all things. Whenever in your literature as well, if you are going through the only single paper, read it multiple times. Every time you will find some different thing. Because now I think most of this, if you are starting your PhD, it means you are not able to read it in a single time. Because lot of things are there, like new terms are there. If you are going to the Google, search them and you will come back. And till that, if you are come back, that time you will forget what was the last one. So if you are going through the at least 2 to 3 times, I think you will find that what was the beauty that is presented in particular paper. So always think about what are the application we can target there. And again, if you are targeting the application, we have to think over about what is the process flow, what is the way by which we can do the fabrication. Even if you are presenting or if you are publishing a paper as well, you are still, if you are doing the simulation well, and if you are writing a one para about your fabrication, definitely it will impact your publication. Even reviewer also get impacted by that. He has some basic understanding about the particular device. So overall, if I want to classify these nanomaterials, so I can classify it into 3 ways. One is carbon-based nanoparticles. Already we have discussed a lot of things about that, like graphene, that is the hottest example we can see here. And some more carbon-based quantum dots also we are using there. Have you heard about the quantum dots in solar cells? Have you heard? Yes. Nowadays, we are introducing some quantum dots of the carbons in solar cell only. We are getting that good response. Like if you are earlier, you was getting the response of 20%. Now we are getting the around 32, 35%, 33, right? So this type of the response we are getting if you are using the quantum dots here. Again, how to define the size of this particular quantum dot? What are the configuration or what are the particular architecture we are using there? That has to be clear to you. The second type of these nanomaterials, that is inorganic nanoparticles. Some classification of these, that is pure metals based. So normally we are using the gold nanoparticles. Again, it is a costly, still we are using that. What is the beauty of these? Anyone? Yes. Basically, it is not easy to oxidize it. So that's why normally we are preferring. Again, it is a costly, but still we are working with the only with the nanoparticles of gold only. Similarly, we are using the some AZ particles also available. It depends upon what is your requirement. For example, if you are looking for some device that will be used only single time, so that time you can use the AZ based or silver based nanoparticles. But if you want to use multiple times, so most probably we will prefer to use that gold based nanoparticle. Now these days we are also having that some titanium dioxide nanoparticles that are giving the equivalent, or I can say about the equivalent property of these gold particles. Again, we have to focus on that, whether it is what is the requirement of yours and what is your targets that you want to achieve there. Similarly, in case of the metal oxide, zinc oxide, titanium oxide, or some ferrous oxide, or Al2O3, these are example of the nanoparticles. Again, I am telling you, don't confuse with the like in the MOSFET based devices, we are using the Al2 through silicon dioxide. These are the some bulk material. Always we are looking for the higher thickness of them. But if you are using at the nanoscale, that time we can use the similar type of the nanoparticles in the replacement of that. Some ceramic type, or I can say insulator type also, or inorganic nanoparticles are there, that are silicon dioxide or zirconium dioxide. And the last one, that is the organic nanoparticles. I think already we have seen 2 to 3 examples. That is RBC. These are the example of these such type of the particles. And about the different type of the proteins are there also comes in this particular category only. So this is the broad classification of these particular nanomaterials. So already we have discussed what are the important characteristics of the nanomaterials. One is the size, second is the shape, third is what is the morphology. And one more thing that I want to introduce here, what is the unique feature of the nanomaterial is that the surface is easy to modify. It means according, like in the last example, we were using our most health-based device as a biosensor. So directly, if you are introducing any bioalgal to our transistor, it will not detect it. It means we should work on that any layer that will bind these particular biomolecules. It means it has to be first functionalized. After that, we can use them. So normally we are using the some antigen or antibody bindings are there. So whenever you are targeting the any type of the binding of the any biomolecules, always first you should fix the what would be the our functionalization surface. So these nanomaterials having the property of easy to functionalize, so easily that can be functionalized and easily they can observe them. Like most of the time, if I am talking about the nanomaterials get popularity due to the surface area only. In the nanoscale, we are getting the large space surface area as compared to the, if I'm talking about the bulk material. So that's why we are getting the higher connectivity. That's why we are getting the higher sensitivity in these particular devices. So these are the some physical property and some chemical properties are there. So basically going through this physical and chemical property that will help you whether what type of the nanomaterial we have to select there. Okay. So like if you are targeting the some devices which require the some strain or stress. So this type of material we are targeting for the piezoelectric material. So that time according to that we have to choose this particular chemical property, and similarly we have to target the some physical properties. So the next thing that is nanoparticles or nanomaterials application area. I think now you are able to give the any multiple example of these. Is it fine? In the environmental protection we can use it. What is the example we have gone through? Air filter we can use. The last example we have said ZIF, that based nanofibers are there that can be used for the mitigation of the pollutants. Okay, but problem is here also one problem is there, like if you are using, like for example nanoparticles are the some spray like solutions are there, like I can compare with the some paints. So easily someone can come here and he can spray there our paint, so it will be painted. So similarly the same nanoparticles or similar solution that we have prepared in ZIF, that can be sprayed on the walls of our room as well. So it will capture our all the PM particles and it will be collected on that. Okay, but problem is that it has to be washed, otherwise sometimes its efficiency would be degraded. So it is ordered that if you are washing with the water, so it can be cleaned and again it will function as it was working earlier. But when you are washing that, so the chemical composition would be there, because all the whatever chemical composition had been collected by our thin film or our pen, it will be go into the water bodies. Again it will be it create a contamination there. See, we also have to think about the byproducts. So still we are struggling for that. What are the substitute we can prefer here, and what are the different thing we can do to remove, or we are trying to change this byproduct. Like sometimes you will find some byproducts that may be useful for the agriculture purpose, but still we have not obtained any particular solution for that. Still we are struggling for that. How to change this particular bioproduct so that can be useful for to other industry or other some agriculture events that can be used. Okay, if I'm talking about the healthcare, have you heard about the nanorobots? Have you heard about? Or in the drug delivery also we are using the some nanoparticles. Directly they will launch in our vein and directly go to that targeted location. It will repair that. So now whatever type of the medical science growing with the some nanoparticle, it is a very I can say it is a good way, and most of the time nanoparticles we are looking for the human being only, because our target is we want to be supreme. So whatever the research is going on, always towards the human being. We want to live a long life using this particular devices. Similarly, in the biomedical research also, so you can compare with like we are using the some X-ray machines. If we are like in X-ray machine, we requirement of the power that is different. But if you are using the thin layer of these particular nanomaterials, so that time requirement of the X-ray source is very limited. Or sometimes you will find that we are not using the X-ray, but whatever the imaging we were getting through the our X-ray, we can get the similar type of image through the nanoparticle layer. So you can think in this way also. And already we have discussed what are the application of this nanomaterial in the electronics. We have done? Yes. Basically, earlier I have discussed about that. We want to replace the channel between source to drain by using the graphene, because in case of these devices also we are looking for the high conductivity. Whenever you are getting the high current, so it will be easy to observe there. So we are looking for the devices which use the similar type of some materials that can work as a highly active or highly conductive channel. Okay. So now these days we are also working some devices that are totally dependent on the tungsten disulfide. Again, tungsten disulfide, again it is a 2D material that normally we are preferring. So just basically covering all the aspect of the nanomaterial in a particular lecture, it is not sufficient duration, but I will try to give you the glimpse of that, or just I want to ignite you what are the different domain in which you can work. You can think over that. So according to your requirement, you can select particular and you can focus on that particular application area. Like in the construction side also, we are using the graphene in the road side. Whatever the cement we are using nowadays, its efficiency or durability may be improved if you are using some graphene dioxide or some composition of the graphene if you are introducing. The similar literature you will find if you really gone through some Google Scholar all thing. And in the in the consumer market also, I think you can give example. Now some beauty products are come with the zinc oxide. Have you heard? Some beauty product, whatever, like some facial creams we are using, that are comes with the zinc oxide nanoparticle only. So already it is in the market. Whether you can check whatever the ingredients they have been used for the development of this particular beauty product. So mostly they are using some zinc oxide particles because it is very glowing. So they are using, you can check them. In the agriculture as well, can you give an example of these 2D materials? 2D material, or we can say discuss about some nanomaterial. Any example? Earlier we were using some urea to enhance the production, but now we are using some spray of some particles that are very I can say that is very good. If basically the urea was impacting the environment as well, it is also harmful to us, because if you are consuming the large number of the urea, or you can say the percentage of the nitrogen is going increase, it is again harmful to us. So now they are trying to replace the urea is coated with some nanoparticles. Have you heard about that? I think a neem based urea coating already government of India has launched that. So that is coating is only improve the productivity, but it will not affect our health problems. So that would not be a health issue for us. So the similar type of the coating we are trying to use there. Similarly, in the automobile industry also, we are applying some coating on the surface of our cars or any vehicles. So that is very resistant to our environmental conditions. So it would be long lasting. So these are the different area in which we are working. Especially, I would like to target some energy sources, because it is the high time to target this energy based domain. I think mostly you are familiar, already we have discussed about the energy conversion, that in the solar cell we are using the 2D nanomaterials. Similarly, one more important part, that is the energy generation, because the energy requirement is demanding rapidly. So now we have to, it is a high time we have to focus on how to generate this particular energy. So now these days, if you are going through I think a particular industry like shoe industry, they are working on some piezoelectric material. I think I'm standing here around 40 to 45 minutes. If I'm using the piezoelectric material, so some power would be generated, and that same power would be used to charge my mobile phone. I think similar type of the products are already available in our market. because basically these piezoelectric material having the property, if you are applying the some pressure, it will generate the some charges. Okay, so there is no need to work on too much on that. Directly some pressure sensor or some, I can say, piezoelectric sensors are available there. You can buy them, you can design your internal circuit, because already I think most of you are from the electronics only, so you can design the small circuit or you can use them easily, and they are not very expensive, around 50 and 100 rupees nearby, you can buy them. So similar type of, I think, in the some toys that comes in this particular, they are using them. So there is no need to supply them any battery cell or things, they are using them. So you can target different technology like a triboelectric or thermoelectric as well. And one of the most important part, that is that we are using this the nanomaterial for the supercapacitor. What is the supercapacitor? What is the supercapacitor? It is a very bad thing, because government of India also thinking about the forming the any policy on these things. If our government in thinking, it means we should be ahead of that. Basically, whatever the charges sales we are using in our vehicles, it first it should be charged. It means it has to store some charges. Okay, whatever capacitor we have that are very having the very limited scope to charge them, it means how to improve the efficiency of them. So the picture of the supercapacitor comes in this category. We are using the similar type of the capacitor only, but we have to modify its internal structure using these nanomaterials to improve its efficiency. Okay, so that's why we are using the some different oxides, whatever the oxide, different type of oxide we have, we are using them to modify the or to improve the performance of the our supercapacitor. So nowadays we are using the lithium ion batteries. Again, we are also working on that to how to improve the storage capacity of these particular materials. So most of the time, these batteries are also part of this. If you are using like supercapacitor is only for the storage purpose. If you are using the some batteries, how to use them? We want to improve the life of or lifespan of this particular battery. So that can be improved through the these different application of these different oxides or different type of the nanomaterials. So these are the broad application area of these particular nanomaterials. You can target any, or if you are working in any particular area, you can target with these particular nanomaterials. So before the next session that I want to start here, that is how to different type of the fabrication technique that we are using for the nanomaterial. The similar technique we are using for the semiconductor devices. The similar technique we are also using for the MEMS devices. So I have tried to here to include whatever the fabrication techniques that are very common here. Okay. So basically, what is the problem with us? Because in our India also we are targeting the different technologies, but we don't have the any skilled manpower who can work in the semiconductor industry. So can I taste any knowledge about your fabrication? Can anyone help me to how to? I think most of you are familiar with the diode. Are you familiar with that? So you have to tell me what are the process flow and what are the things has to be done for the fabrication of the PN junction or the any diode. Can you think about that? Are you aware about that? In the fabrication process, whatever you know, you can tell me. Just I will try to recall it. Only scratch only, because creating the content is not the fabrication. I'm talking about the PN junction only. It does not require any MOCVD or thing. Take 2 minutes. Just I want to know if you are the electronics engineer, if you don't know what are the fabrication process and how to develop.
doping prospect. So we can dope like if we are using.
My question is that just I want to fabricate the PN junction. Okay. What are the process flow you will use that? Just tell me. Basically, that will help me to understand what is the actual thing I have to be covered in the next. Can anyone? That is fine. If someone asks you something about like what are the ingredients are required for vegetable, you can tell. What are the ingredients are required to make a vegetable? It means you first you should initiate with the what are the important things that has to be there. ये तो बता सकते हो ना लगभग सब. Salt, pepper, and chili. So similarly, you have to think all like if you want to fabricate the semiconductor device, what are the important things that has to be used? Okay, first thing that is the substrate on which we have to fabricate it. The second, oxidation. Implantation is fine. It means it is the stage where you don't know anything about the fabrication. And if you are really working on any type of the devices, or that time if you are not thinking about how to do the fabrication, so this is not the correct way of doing any research as well. If you want to say I am an electronics engineer. I have a question. Yeah. Actually, I am confused. Like you want to fabricate or you want to grow? There are two different terms: fabrication and growth. So if we want to fabricate, that means we want to make a contact. I think you are not comparing very well, because if you are talking about the growth and the second is one is the growth, second is the deposition. These two terms are different. And after fabrication means we are making contact on top of the layers. So that's it. I think you have to go through the some basic of the fabrication. What is the fabrication? I think if I want to classify any device, so I can classify simulation part. First I have to do. Second is that simulation. Third is the sorry. First is simulation. Second is fabrication. Finally, it has to be tested. These are the three stages if you want to develop any device. So already you have done the any simulation, because some diode is very mature technology nowadays. So simulation is already okay with that. So it is not required any simulation as well at present time. Just you have to tell me if I want to develop any PN junction, any diode, what are the steps that has to be followed for the fabrication. So fabrication is a complete tree, which having the different branches, like whatever you are telling. In my knowledge, what I'm saying, first we have to take a substrate, then we grow N type, then we grow P type, then after we will make contact. Means we have created the measure to go through the N type or P type, whatever is the nearer to the substrate. We have to create the measure. Then we will go for the photolithography to fabricate a contact. So this is the flow in my knowledge. You are somehow around this 50% now. You are fine. Earlier you was, I think, or 25 was fine. So now you are fine at least 50%. But in my perspective, yes, growth and I think he will help.
Like the substrate identification, then we will go for cleaning, then additive processing is there, then lithography process, then subtractive processing, then last process integration. We have to see whether all the process are done well or not. At last it's completed. This is the general process for all the fabrication. Like suppose we are fabricating anything.
That is the generalized process that we have to adopt there. It means if you really want to fabricate any device, so first we have to choose the substrate. What would be the substrate? So now these days, whatever the devices that are existing with you that are silicon based device, it means the substrate that we are using here, that is the silicon only. But problem is that, like, just I will give you the 2 minutes. In 2 minutes I will try to cover it. That in the PN junction, what is the PN junction? It means in the one section we having the some N type of the semiconductor, in the second part of we having the P junction. Okay, it means if I looking for the some generalized process flow, it means initially I want some silicon substrate, and after that I want to grow the some N type or some P type. Okay, and already I think you know how to create the P type or N type. We have to introduce the some doping. But problem is that whenever you are looking for the indoor semiconductor, that is the silicon, it is not possible. It is a very high cost, so it is not possible for a like our we cannot buy them. It means whatever the wafer you will find in the market, that would be from P type or the N type only. Okay. So always whatever substrate you are using there, that would be either P type or N type. So if you are using the silicon, that time it is fine. We will go with the N type, and after that I will introduce some P type doping, and finally I will grow that whatever the step you are telling, I will take. But sometimes you will, if you are using the sapphire substrate, so there is no scene of P type or N type. You can use directly. It means first we want to grow that P type, N type, and finally once junction would be there, then we can create the contact. That would be the process flow for the fabrication. It means finally, if I want to tell you, first selection of the substrate, okay, and after doing selection of the substrate, what I have to do? I want to deposition of the P type, deposition of the N type, and finally I want to check whether whatever doping you have target, really you are getting out that. It means first you will select the substrate, after that you do the deposition of the P type. You have to ensure that whatever the doping level you have target, you are getting out that. It means it has to be characterized first. Okay, and after that, if you are satisfied with that particular process, again we will go for the deposition of the N type. Okay, again it has a big story about how to create the N type or how to create the P type, but you should go for the next level, that is the N type. Again, it has to be tested whether we are getting the equal or right doping or not. Once if you are ensured that we are getting the correct doping of that N type or P type, we can go for that contact. Okay, once you have done the contact also, again the contact also be tested. Whether we are whatever in the contact also we are getting to some resistance, whether it is comfortable for our device or not. It means these, and once it is, you have tested it, it is fine. So that is the process flow of the fabrication. So whenever if you are targeting any device, that time you should ensure that whether whatever thing you are doing simulation, whether it is feasible or not. The same thing if I want to, just I have included one example of silicon. Okay. Here you can see, this is the particular fabrication process flow that I have included here. So I have initiated with the N type of the semiconductor. And after that, I have done the growth of N type of the semiconductor. So directly it is not feasible to do the deposition of the N type. It means first we have to introduce the pure semiconductor. After that, it has to be doped. Okay. And third step, that is we want to oxidize. This oxidize only for the purpose of the masking, because basically in the next you can see in the D part, you can see by using the some lithography process, I am opening this particular area for the P type of the doping. And finally, once if this after doing the lithography in the etching process, I will this particular cavity is opened here. After that, you can introduce the doping layer. So earlier, what was that? N type semiconductor was there. Now you want to convert into P. It means again I have to increase the trivalent atoms if you are comparing with the N type, because earlier we having the N type of the semiconductor. Okay. So can anyone tell me what is the purpose of using this particular silicon dioxide? Passivation, that is fine. We can consider here, but mainly this silicon dioxide we are using only for the purpose of a protect only. because only this particular area only I want to deposit. I want to introduce the P type. So the remaining part should be protected. So that's why it is called the masking layer. In the last, we are not removing this particular oxide because again we want this particular silicon dioxide as a passivation layer. So the same process flow was, for example, this particular fabrication process flow was introduced by someone. But the same thing, if I want to modify it, what are the things I can modify there? The process flow is there. If someone asks you how to modify it,
masking and then apply it like light wherever we want those area to be, then after we can.
any step that you can skip there? Do you think any step we can skip? First two step. So without selection of the substrate, how you can move towards the C?
No, after this only.
Yes. If that was the someone proposed this type of the fabrication process flow. If you want to modify it, if the same thing if I want to do myself, so what I do, I will skip the B. It is not required here because N plus is already there. I will introduce the oxide directly, and after that I will do the opening of that, and finally I will increase the doping, so that will overcome to the N plus. So N plus already is there, P plus I will introduce, so junction would be there. So this particular B step can be removed here, and the final or the remaining steps would be there. So this is the process flow for the two terminal device. If you are looking for the transistor, so the process flow would be different. So that we will not here, but you should have the some curiosity about that key. If you are looking for the any type of the devices, how to do the fabrication of that. And now there's some like government initiatives are there. Through them you can approach the some institute. They are providing the such type. They are having the some particular facility like INUP program is there. So you can approach them. They having the sub facility. Just you have to submit such type of process flow, and you can go for the fabrication. And finally, they will that is their guarantee. They will produce the particular result, whatever results you have targeted there, because they are very expert in them. Because a one single person or single technical person attending the single any particular instrument only, so they having the expertise on that. The same instrument, for example, I have, but I will take too much time to optimize the particular recipe for our device. Huh? No, sorry, it's a planar device. Okay, whenever you are going, just
growing in the C direction, right? That's what I'm asking.
Yeah, whenever you gone through the any fabrication process, you will find the two type of the process flow. One is the cross sectional, okay, or somewhere you will find the, I can say, cross sectional and top view. So whatever, this is the cross sectional view is there. So if I'm going through the some top view, that would be different. So it is lateral only, vertical only. Yes. So the broadly, if I want to classify this particular fabrication process completely, so always we will start with the selection of the substrate, and after that I will target the how to clean that, because cleaning or maintaining the overall clean room facility at our, and that is again it is a important part. If like if in the last also in the fabrication of this particular PN junction, we having the 5 to 6 steps are there. In the any step we are getting the any type of contamination, you would not get the results. So there is the meaning of, or I can say, doing this particular complete process, it doesn't have any significance. It means each and every step it has to be monitored properly, and we have to ensure that whether we are getting the good performance or whatever the desired performance are there, we are getting or not. Okay, so first thing, that is we have to select the substrate. After that we have to clean it. The second step, that is whatever the deposition technique that are required for mostly for the semiconductor device, the same thing we are using for the some MEMS device, the same we are using for the nanoscale only. But problem is that if you are looking for the semiconductor device and the MEMS, we are working on the micro scale. And if you're the same thing, if you want to use for the nanomaterial, that time we have to optimize whatever the recipe we are using for the deposition only. It means the tool would be same, but we have to optimize the recipe. How to how to ensure that whether we are getting the nanoparticles or not. So normally, if I'm talking about the synthesis of the nanoparticles, so we are using these two techniques normally. One is the top down method, that is always we will start with the bulk of the material. Again, we will use some mechanical process or some lithography process for to convert this bulk into the powder, and finally it has to be converted into the nanoparticle. Okay, the second approach, what would be the bottom up approach, in which we will start with the some nanoparticles. We will go to the according to the application area of the cluster, and finally we will create the nano levels. So atomic level to cluster, cluster to nanoparticle. This is the way by which we will use the synthesis of this nanomaterial. Okay, so it means two methods are there. It means we have to we have a choice whether we will go for the top level, we will go for the bottom level. What is the good way to choose? So normally in the academy we are going towards the bottom only. Okay, but industry persons, they are always looking for the top to down method, because they having the extensive facility to how to use, because buying the bulk is very easy, but if you are buying the this nanoparticle, it is very costlier. So industry person always they are looking for the top to down method, but in academia always you are looking towards the bottom of approach. So this is the way of synthesis. Again, conversion of this atom to cluster also it requires the particular chemical or some physical recipe as well there that has to be followed. Okay, and similarly if I'm talking about cluster to nanoparticle, so using this particular bottom up method, we have tried one particular example of fabrication of the graphene zinc oxide heterostructure based flexible and thin platform based UV detector. So already existing devices, whatever the UV detector we are using now these days, that is the based on the this particular, like this is the PET substrate there which having that ITO coated, so bottom electrode would be there, and after that we are using the some zinc oxide of the 100 nanometer, that is the thickness of that, and finally we are using the AG as a top electrode. So now by using this you can detect that basically two terminals are there, bottom and tops are there, you can use that as a electronics device, or if you are illuminating any type of the UV source, how this response of the electrical response of this particular device is get modified, that can be observed. Okay.
Is it MSM kind of device? MSM kind of device.
What is the MSM?
Semiconductor metal.
You can say. Okay.
So we are creating interdigitated electrode or some.
No, this is the normal electrode we are using. Basically, or normally, if you are preferring the interdigital, that time only if you want to increase the sensitivity of the area, like in the gas sensor, we are using that. Okay, this is the normal we have targeted here. Basically, in at that particular case, we are not so using the any type of the, I can say, metallization technique. Directly, we are used the silver paste, and we are fixed on the this zinc oxide material, and
Just a silver there and you are measuring this.
best. Directly, we have not any particular tool for the metallization. The same thing we have repeated with that. If you are using this PET substrate, after that we are growing this graphene, and finally we have done the zinc oxide and the AZ. Dimension of it?
Like you are mentioning that 100 nanometer is
there. Yeah.
So how we are going to be precise?
Basically, in this particular case, we have used the spin coater for the spin coater. In the spin coater, basically we having the 2 to 3 important function, that is at what RPM you are rotating it. So according to that, according to the viscosity of the solvent that we are using for the zinc oxide, okay, it also important. So first we have to optimize it. What is the thickness we are getting there? So for the same also we are using the some thickness measurement tools are there. So you can measure, like if you are getting the if you are using the RPM of 10,000, so that time whatever the thickness, if you are using the 5,000, what is the thickness we are getting? So there is some proportionality we can do, and we can calculate it.
That optimization is okay, but how we come to know, like we have to grow or deposit some 100 nanometer only, 50 nanometer only? How can we decide?
That is the part of the simulation. that has to be done in the at the stage of the simulation.
In simulation, and somehow we are correct, but it is not possible. Like every time, it is not possible. Like if we are getting correct result.
No, basically whatever the observation I have made, that is if you are going for the simulation, that time you are getting the 100%. So if you are using the same recipe or in a good way, you will get the 90%. So mostly 10% variation is there, but getting the 10% variation, it is not the big deal, because in the whatever the thing you have simulated, and if you are reproducing it and you are getting the 90%, again it is a very good. So we can do that. Okay, so whatever things we have used, that I am telling you. So basically I have tried to introduce the graphene is there, but problem is that graphene cannot be, we don't have the any nanoparticle of the graphene. It means it first it has to be grown. And how to grow that? Normally we are using the CVD process. If you gone through the any literature, you'll find that CVD, chemical vapor deposition. It means we are using the methane gas as well some other compound of the carbon in a particular vacuum as well the temperature level, and it will convert into a graphene. Again we have to focus on whether we are getting the single layer, double layer, multi-layer. Okay, so that has to be targeted. So normally if you are using the CVD process, that is not a particularly in a controlled manner, you will guide like around 5 to 10 layer thickness of the 5 to 10 layers, you will find it. So the same we are used here, and we have tried to it really whether we are getting the good performance or not. So first the C section that you can see, that is the SEM image of this particular zinc oxide. Why we are doing this particular characterization? Because we want to ensure that whether whatever the thickness or whatever the zinc oxide we are using there, is there any voids, is there any defects are there? Sometimes you will find that you are going through the any process, or sometimes you are not getting the uniformity. The result would be totally different, because it requires some uniformity of that. So first we have to ensure that whatever the process we have adopted there, is it fine or not? So that's why we have gone through the SEM image. So here you can see this type of the grains we are getting in the zinc oxide also. So that will help us to ensure that whatever we have grown, that is the zinc oxide only. Okay, and for the graphene case also we have tried to whether we are getting the uniform layer of the graphene or not. So that also ensured through the SEM image.
How about the interface?
How
we can check the interface?
Are you asking about the surface?
Interface between two layers. How we check if it is homogeneous?
Okay, you are asking about the addition of that. Okay.
So how you will check the uniformity?
Normally we will not prefer to check the uniformity between layers, because whenever you are targeting, we are checking only the addition of that. Like first is that PET substrate is there, we want to deposition or we want to apply this particular graphene layer. So first we will ensure that whether we are getting the addition of between these two layers or not. Once it is we are confirmed with that we are getting the good addition, it means already it is aligning with the texture of this particular PET substrate.
Substrate layer is fine, but if you have a second layer, it will be difficult to know because sometimes the third layer can merge inside the second layer, and you have to know.
Yeah, right. Basically, sometimes if some voids are in the graphene layer, so there is a possibility. But when you are going to the layer to layer process, that is a common process.
We have to ensure that there is no migration between these two layers. How we will check, because it can.
So this is the way by which that is the lattice matching process we have to do. So
even after that also it can happen.
You will get that. That's why that
is matching. You can in with the bottom layer, but once you are going layer by layer, that will be.
No, we can follow that. Basically, in the last also we are working on the gain-based devices. So it was very easy. We will take the substrate of the gallium nitride and directly we will apply the gallium nitride oxide. But it was not easy. That's why we are using the different stack of the layer, like aluminum nitride. Somewhere we are using the different doping level of the gallium nitride. So that is the part of the optimization of the stack only. So here also what we are doing, just we are trying to, once this particular graphene is applied there, we will ensure whether, basically why we are checking the uniformity, it means there must not be any type of the crack or any type of the void. So there is the chances of breakage of this particular layer. Once you, if you are ensured through this particular graph, it means we are getting the uniformity there. So directly there may be the chances, like somewhere we are getting the graphene thickness of 2 layers, somewhere we are getting the 4 layers. That would be the probability. So we have to consider all the things, because in the fabrication process we cannot ensure that. If you want to ensure that, we have to go to the highly sophisticated equipment. You can use for the TM. You can only analyze the TM is also sufficient. We can ensure that. But again, I am telling you, TM also give you the information of the grain size. That will not tell you the what is the structural or surface of that.
Check with the how interlayer is matching.
That can be analyzed with help also SCM, like in this vertical device also you can break it, and vertical also you can check, but still you will find the some voids in between that, because it is not under the control of that. You can do again. HRTM is a very sophisticated instrument. Most of the time you will not find it, but same is easy to, you can find it. I think in the Raipur also, if you're most of the institutes are there, you will not find it. FMB also we can. Again, AFM and SM both are the surface morphological tools we are using them. We can use them because doing the characterize, that is good thing, but we have the limitation. A single layer can be characterized in the many way, but according to the availability of that and according to the application, targeted application, we have to fix that. Whether we will go for the TM, we will go for the SEM, we will go for the AFM, or XRD is sufficient for that. So according to that, you have to fix it. So these are the process particular parameters that we have used for the growth of this particular graph. Again, this optimization of these parameters, it's a very tedious task for us. So mostly who are working in this particular domain, they know, or according to the specification of our CVD tools, they know what are the features, what is the flow rate of this particular gas. We can use that. So you can use, so this particular parameter again also depends on the particular equipment you are using. If you are using the chamber size is different, so that all this particular parameter ratio would be different. So whenever if you are going through such type of the growth, always try to contact with some person who are really handling this type of the process flow. So
you are using 3-chamber CVD or 2-chamber CVD?
2-chamber only. Normally in case of the CVD, we are talking 2 John or 3 John, not say chamber. So these are the AFM also we have, by using the AFM also we have trying to ensure that we are getting the uniform surface or not. What is the roughness of the grain sizes that we are getting. In the FM also we having some tools that can be used to analyze what is the grain size we are claiming here, that is a nanoparticle. So you have to ensure that whether we are getting the nanoscale, the nano dia of this particular material or not. So that can be ensured through our SEM. I think image who are working this image, they also we are using to analyze the grain size. What is the grain size? What is the average size of the grains we can analyze. Similarly,
shape for the nanoparticles. Shape for the nanoparticles.
Shape we cannot say anything about the shape. Only that depends upon how our electrons are assembling themselves.
For example, ZN is cubical, hexagonal structure.
No. Basically, crystal structure is the different thing. Okay. If you are again, if you are really targeting any type of the material, so a lot of crystal orientations are there. So according to the crystal orientation, different size would be or shape would be different. So it depends upon what type of target you are doing there. So directly we cannot say what is the size of the zinc oxide. A different classification or different class crystallographic structures are there that has to be optimized or that has to be chosen according to your application area. So similarly for the textography, crystallography also we can use some XRD to ensure that whether we are getting the correct orientation of that. Again, orientation is it's an important parameter. Because in case of this particular selection of this unsold this oxide was 002 only, because in this particular domain only it will work as a responsive, or I can say it will work as a good good piezoelectric material. So we have targeted that, and according to that we have fixed it. So first we have to ensure that what is the XRD orientation of that, and using this particular graphical representation we can analyze the multiple number of a parameter. Like we can analyze that. Yes, I have included in the next. We can calculate the what is the grain size. The same thing we can use that. We can calculate through the SEM. We can use the TM as well. We also able to calculate the what is the stress that is generated through our layer, because stress analysis is also an important part if you are going through the layer to layer fabrication. So it can be done through this particular. So Raman spectro, again, it is an important part, play an important role if you are working on the some 2D materials. So basically this Raman spectro will give you the information whether you are getting the any defect, what is the actual defects percentage in this particular, the ratio of like 2D band or the G band, that will help you. What is that?
Layer also we can identify.
We can identify it. So mostly that's why I told you it is around 5 to 6 or 5 to 10. We cannot ensure that.
Which band we can ensure like our layer is not stressed or strained?
In case of this, yes.
I mean, which layer? I mean, for example, if I'm doing Raman of aluminum nitride or gallium nitride, so with E2 high mode we can identify like it is stressed or
Stressed or not.
Right? So similarly for this, I mean, these are the different bands.
Only bands are there.
Right. So using which band we can identify like our grown layer is stressed or not?
Not. Okay. Normally by using the Z band ratio of the 2D or Z band, we can analyze that. And if you are targeting for the stress only, Z band should be very sharp. So according to that, we can ensure that.
That to the FWHM.
Again, if you are comparing with the FWH, it means we have to go towards the XRD.
If is too high, that means stress. No?
That is fine. So, but normally for the graphene, we will not go for the XRD. FWHM only provided by the XRD. But for the zinc oxide or whatever the material we are using, which having some crystallinity, that we can go towards the XRD. But normally, if I like such type of graphene like dioxide, we have to go towards the Raman spectroscopy. That will help us to determine whether it is fine or not. So that's why according to the application area, we have to target it. So EDS also available, that will help us to ensure whether whatever that our particular thin film is pure or not. If you are getting the different type of the percentage composition of that, you can ensure that whether it is pure or not. So EDS, again, it is a part of our SEM also. In somewhere you will find in the XRD as well. So that will give the detail about the elemental analysis of that. So these are the UV detection results we have obtained under the dark current and under the illumination current. Again, in case of the UV detector, two important parameters, that is the that is the responsivity and the detectivity. So that two important parameter has to be calculated here. Otherwise, there is a lot of different parameters are there, because it is a normal two terminal device is there, we can analyze. But for the considering this UV detection, we have analyzed that if you are using this particular graphene, we are getting a sharp variation in the under the condition of the illumination, and it has been compared with that. In this way, we have obtained the responsivity of 0.49 and detectivity of this. If you can compare this particular with the existing literature, you will find it's a very nice contribution towards that. And one more thing that
this emission current is lower than dark current. The leakage is more. How you can say like it is a good use?
Yeah, basically we want to detect that part. It means detection. It means we are looking for the variation in that range. Like earlier you was getting the 10, and now we are getting the 5. It means variation is good. So now this is the detector. We are looking for only the what is the percentage variation in the current. The reference is our, in case of the dark area, that is the reference for us. So how much earlier we also, I have not included the graph. If you are doing the same thing with the earlier device, that is the existing device. So that was the difference. In that time we are getting the very less, like somewhere we are getting that. But according to that, how much variation we are getting? Basically, our target is not checking the functionality of the device. Our target is whether our device is able to detect the particular intensity or not.
That will detect something else also. And that is a noise, na? That leakage current.
Okay.
So that's what I'm asking.
Yes. Basically, if you are looking for the any device, so you have to target the any like application area. Like earlier, I was working on the GaN-based sensors. That time I was thinking only for the ID current and the VDS only, or ID current and the VTH only. That is the threshold voltage. But now, if I'm looking for the same thing for the power electronic, I'm using the same device. But that time my approach would be different, because that time I have to target the high breakdown voltage. Are you getting me? So according to your application, if you are talking about some RF application, that time I have to consider what is the capacitance, what is the leakage current is there. That has to be considered here. But in this case, my target is I want to detect what is the really our device is working functionally, working fine under the UV condition. That has to be there. This is not my concern. My concern is that my oscilloscope or my semiconductor analyzer is really detecting the UV detection or not. So according,
just check it, like whether it is working or not, that is fine.
Basically, according to the, if you are working on the RF device, that time you have to concern about the some noise figure. You are also concerned about the some what is the bandwidth ratio. That has to be considered. But in our case, we are not focusing on that, because according to target, we have to optimize the particular things. So basically, why we are getting this type of the variation, this also can be understood through this energy band diagram, because energy, this graphene is providing the some intermediate Fermi energy level. So that is supporting us to more number of charges that can be moved from our surface of the zinc oxide towards the electron. So that's why we are getting, because everywhere it has to be justified whether we are getting the results, really it is supporting to the physics that are available. Yes. So the next one thing that we have skipped, that was how to do the thin film deposition of these particular materials. So broadly, if I want to classify all the materials that are available with the nanomaterial or some different micro scale material as well, so it can be classified in two ways. One is the physical process that we are using there. Second is the chemical process. So in the physical also, it can be classified into two, that is vacuum and the sputtering. In the sputtering also, we are using the vacuum. But in case of the vacuum based technology, vacuum having the particular role there. Only what we are doing, or we are introducing the species and they will react there, and finally according to the level of the vacuum, it has to be react them, and finally we will get some thin film, right? But in case of the sputtering, the vacuum having the less role as compared to the whatever the parameter that we are using there for a sputtering process. Okay, in case of the chemical process, it can be classified in two. One is the gas process, second is the liquid phase. In case the gases process also, we are using the CVD process, and different type of the CVDs are there according to the requirement. Like if you want to the chemical process at the level of the atmosphere pressure, it is possible. We are using some low pressure. That time some according to the requirement of our material, we have to choose what type of the chemical process we have to use there. And some liquid phase also, sol gel and the spray pyrolysis we are using. We can use the dip coating as well. These technique also may be used there. So just I will give you some brief introduction about that. What is the difference in the evaporation method and the sputtering method? So basically, its name indicates it is the evaporation. It means only first we have to put our sample in our crucible. So we are using some heating element that will help us to evaporate this condensed material into the chamber, and again it has to be condensed on the substrate. It means basically in the physical process we having the two stages. One is the source, second is the collector, or I can say substrate that where we have fixed it, right? So whenever you are first initially we having the solid material is there, so we have to use some side, like if you are using the some temperature, it means it is a thermal process is there. So by using this thermal at the melting point, this particular material has to be evaporated in this particular chamber. Okay, and once it is evaporated, it has to be fixed on our substrate, and it has to be condensed there. So it will be again it has to be converted into the solid material. Is it fine? So if you are using the same source for the realization, or I can say conversion of this solid to evaporation, if you are using the electron beam, so that time it is called the electron beam evaporation process. It means according to the source of the heating or source of the these particular ejection of this material, it will decide whether it is a thermal evaporation system or it is a electron beam evaporation system. Okay, but in case of the substrate, in this first we have fixed our this is our target is there. Target is nothing but it is a source of the our particular materials. We will apply the some inert gases that will come into the due to the some we are applying here positive voltage there. This is the grounded there. So due to the high electric field, these inert gas ions has to be converted into ions, and that ions will be stacked on this particular our target material, and it will eject the some these atoms, and these atoms should be deposited on the our substrate. Okay, but what is the beauty of this sputtering process? It is a costlier process if you are comparing with the CVD, but in this particular sputtering method, we can control the process. We having the any controllability of that, so we can do that. So this is the one optical image of our system. That is, this is the particular control unit is there, and this is the chamber of this particular sputtering unit, and this is the chiller we are using there. So first thing, what is the who is increasing the cost of this particular sputtering unit? That is the target only, because in case of the evaporation system, we can use the solid particles, but it requires some particular shape of the electrode. So shape of this sputtering target. So first we have to convert our solids in terms of this particular target. So how to convert? Normally we will use the like aluminum if you are using. So we will use the aluminum powder, and it has to be using the hot process. First it has to be converted into the particular target, and after that particular target would be used in this particular equipment. So if it is a 2 inch, so we want this particular target size of 2 inch. If it is a 3, so we want 3 inch. If it is a 4, so according to the equipment, we have to first we have to create this particular type of the targets. So the process of creating, like if you are working on the gold, so that time getting that target of 2 inch, it is a very costly process. But the same thing, if you are having like 1 gram of the gold, so that can be evaporated through the upper evaporation system. So that's why the cost is very important here. So mostly sputtering unit we are using for the metallization. Somewhere we are using the some oxide material as well. We can use them. So already we have discussed that what is the sputtering process. Only that these primary particles will come there, and they will stack there. They will transfer their energy to these atoms of this our target. And somewhere if you are getting the binding energy is more than that, the ion energy of the ion, so that will eject our atoms. And this particular ejected atom has to be deposited on our target, our substrate only. So basically it is a 3 stages process. First, evaporation of the target material. Second, transfer of vapor from target material to the substrate, and finally it has to be accumulated on the substrate. So this particular sputtering also can be used in case of the evaporation. You cannot do the multi-level of the fabrication, but in case of the sputtering you can do. Like if our instrument having the 4 target facility, like in this example you can say we are having the 2 target facility. It means there is some shutter is there, so it will be closed this particular. And for example, if you are using this particular, so that time we will use that, it will close, we will close it. Once our step layer or step 1, or I can say layer 1 deposition, or you can open that. So the multiple layer type of deposition also can be done through the sputtering unit. But again, it is depends upon the what is the requirement, because whenever you are evaporating this particular, if you are ejecting any atoms, all the atoms are deposited on all over the surface of the equipment as well. So whether it is contaminating the previous step or not, we have to ensure that. If you like in nowadays we are using the some other type of the metallization process. For example, for the source and then we are using the aluminum, or after that we are using the gold, platinum. This type of stake we are using to modify the overall work function of the our electrode. So that type of the deposition can be done through the this type of the sputtering unit, because all the metals, so they will not create any type of the oxide, so there is no issue, we can go with them. Similarly, evaporation system also we are using there, same thing we have discussed there. This is the crucible where we have to fix our target material and we will apply the some heater. If you are using the electron gun, it will be applied there. It has to, all the target material has to be evaporated and it would be submitted to the our substrate. So what are the important things that you are thinking that that has to be considered here? This is the vacuum chamber is there. It means first you should take care about the what should be the level of the vacuum, because your vacuum level will decide whether what are the number of the target materials, target atoms that are evaporating from here, that are reaching towards the substrate holder. Normally, in case of the thermal evaporation system, we will not consider the pressure. Only vacuum level would be important part.
What is the general value?
Normally, we can go for 10 to power minus 3 torr, we can use that. And if you are working on that, like in case of the all the processes, we are working on the two pressure. One is the working pressure and second is the ideal pressure. So normally for the working, we are using the 10 to power minus 3 torr we can use there. Okay. So you should take care about that. What is the source of, what is the power of this particular source? That will decide whether how many number of target elements should be ejected from there. And the second thing, what is the level of the vacuum? That will help us to the number of atoms that are evaporated from here to here. The same diagram is there. That is, this type of the crucible is there. This electron will come there and it will help us to eject these particular atoms, and finally it has to be deposited there. So if I'm comparing these three techniques, so you will find that in case of the sputtering, we having the capability of controllability. So that's why we can, it is very easy to control the process, but it is a costly process. But if you are going with the electron beam, again, if you are comparing with that some thermal evaporation system with the electron beam. So thermal evaporation system, again, it is a easy to do, but in case of the electron beam, again, it require a source of the electron. Otherwise, it is a very common for thermal as well the electron beam. But in case of the sputtering, the next part, that is we are getting the uniform layer. So whatever layer you want to, you can grow there. You can control the thickness as well. But in case of that, this thermal evaporation, you cannot control the what is the thickness of that. So in most of the time in sputtering unit, we having the some thickness monitor is also there that can regularly it monitor the what is the thickness is growing there. So if I'm talking about the classification of the chemical process, so this is the chemical deposition method. So sometimes you are using the gas based and second is the some liquid based. So if I'm talking about the gas based, so common process that we are using the CVD process. And what is the CVD process? In this CVD process, only we having the quartz tube is there that is closed from both the end, and we have to introduce that what are the gas or what are the combination of the chemical composition it is required, we have to introduce there, and finally we have to control the temperature and the what is the level of the vacuum that has to be controlled. It means the system, all this particular tube only help us to whether determine what is the recipe is going through, that is only dependent on the temperature and the pressure only. We are not using the any physical method there. So this is the particular thermal system we are using there. So basically it's a chemical composition based process is there. So spin coater, I think it's a very common equipment, so you know that. only what are the things that has to be care. First, how much amount of that solution we are pouring here, that is important. So according to the calculation, some mathematical calculation also available for the spin coater, you can do that. What amount of it has to be poured there, and according to that, and what type, what particular speed of that has to be maintained. So according to that, you will get the uniformity, you will get the thickness of this particular layer, and how these particular arrangement of that these material will be gone through. So it's a very easy, or it's a very cost effective. So most of the time, wherever it is feasible, we are always looking towards that this spin coating process. What is the limitation of that? We cannot control the ambience or environment of this particular process, because it is an open environment process, so we cannot control that. Now there is some instrument are there that are doing at the level of the vacuum, but it is again, it's a very complex process, because first you have to pour the material, we have to maintain the vacuum level. Till now, whenever you are not maintaining the material or the level of vacuum, so it will not work. So it is a very lengthy or complex process there, but we can do that. One more important part that now this is very fascinating, that is the deep coating. If you are looking for the like a some mostly in we are using this chemical solution of these particular chemicals in case of the deep coating as well. But if you want to do the thickness of multiple layers, so we can do that. So basically, this is the particular moment of this is our substrate is there on which we want to deposit, and this is our solvent. So directly it will move down, and after particular duration like 10 second, 20 second, 30 second, you can set there. So after that it will come outside, and it will, according to the temperature environment also, it will go to the dry. After that it will evaporate in the environment. But what is the unique feature? Unique feature that you can go for the particular time analysis you can do there. Second thing, the temperature can be maintained. Most of the chemical reaction are going at the particular temperature only, so that can be controlled through this process. So otherwise it is a very easy to do. So already we have discussed about the X-ray and how to use them. So one thing that we can discuss there, these are some Cheers formula that normally we are preferring to use the calculation of the what is the grain size we are using, what is the ABC, what is the ABC, these are the Miller indexes of that. So by using that we can define. Similarly, we can calculate this particular, we can calculate the defect density by using this particular graph. Okay, and strain and stress also we can calculate that. These are the some important parameters if you are looking for the some stress analysis or similar device of if you are
Screw dislocation density, that simple XRD, general XRD, can we calculate screw and edge dislocation density?
I'm not sure about that because I have already have not done, but I am sure about the defect density we can analyze, but I'm not sure about that. Because mostly I think in the electrons we are not using that. If you are chemical person or say that normally they may be used. What is the application area of you? Photo detector. In the photo detector you are using it. Okay, I'm not sure about that. So this is the probe station AFM process. Already we have gone through that. Yes, one thing that we can discuss here, that is how our FEM functions. So these are the particular, this is the electron guns is there that will eject our electrons that will help us to image this particular sample is there. And this is the anode in which we are applying the high electric field that will help us to concentrate on all the electrons that are ejected from the electron gun, and these magnetic also help us to maintain this particular, or I can say exclude these particular electrons, and this scanning coil and this electron detector also help us to move there. But all the things that in most of the time we are getting the three type of the electrons. One is the secondary electrons, second is the once electrons, so electrons that are ejected from our electron that will strike with our substrate, and after that it will be reflected back. So it has to be collected, and according to the collection of that you will get the SEM images. So similarly you can see this type of the image only captured through this particular SEM. Nowadays we are having the FECM also. So here you can see what is the resolution we can see. Whether it is not feasible to see with the naked eye, but if you are using the similar type of device, we can analyze that very small, or I can say nanoscale device as well at this level. Similarly, if I'm talking about the TM also, it is similar to the SEM, but their difference is that what is the difference in the SEM, the TM? The similar type of analysis can be done, but in case of the SEM, we can analyze the surface only. But in case of the TM, we can analyze the inner planar of planes of our device. Okay, what is the limitation of that? Limitation that in case of the TM, the thickness of the sample should be very small. But mostly, if you are looking for some devices on that are grown on that some, I can say, some electro substrate. So normally thickness of the substrate is high. So that cannot be used here. So first it has to be, it requires the pre-processing of the sample, but in case of the SEM, directly you can use them. So the last equipment, that is the semiconductor analyzer. Normally we are using in the electron device. It's a very common. How to analyze that? If you are applying the some voltage, how much current you are getting there. So here you can see this particular graph is produced through the semiconductor analyzer. So this is the our red symbol, that is the, it is the reference whenever you are introducing the some biological sample there, how this electric current is get modified. So that is basically characteristics of our sensor only. So you can analyze through this semiconductor analyze. We can observe if you are applying this particular type of the biomolecules, how this drain current is get modified, and that will help us to what is the concentration of this biomolecule that has been introduced there. So I would like to last and acknowledge this particular project as an India collaborative research project, and ISM, this IMRE, which supporting us to fabrication of the GaN devices, and Rajasthan State Pollution Board as well. So finally funded for the MOF filter designing, and NIT Raipur also, they are providing the such facility, and our research group who are working very hard to implement all these technologies. Thank you. It's all from my side. If you have any query, you can ask.
Any question? Which one is accurate? I mean, SEM or TE?
The TM is more accurate because in SEM only we are getting the surface morphology, but in case of the TM we are getting the inner layer structure as well. Normally, if you are going with the SEM, we are getting the I can say 2 millions of resolution, but in case of the TM, we are getting the 50 millions of resolution we can get. So it's a very high resolution.
Joule range, I mean, in nanoscale, we can find out in the same.
In the same, if you are going with the like a 2, I can say 2 millions, that is fine. But in case of the TM, we can go up to the 50 millions. That is the resolution range. So in case of the TM, it is a very highly resolution image we can get.
Excel image, we found out the HL. That is from the highest peak.
No, highest to half FWHM, half width maximum of that. You can see. Yes, you can see. This is the highest peak of intensity, and we are looking for the half of that. So here we will measure what is the width of that.
Peaks are available in XRD.
So normally we will go to the highest peak of that. So it is very impossible that we are getting the highest peak, multiple highest peak. Only we will get the similar. Sometimes you will find like if you are working on the silicon die, so the same material having the same peaks, but that would be similar. There is no variation in that.
So that means it is not clear.
This is the polycrystalline. If you are getting this only single peak, it is a crystalline structure. If you are getting the multiple, it's a polycrystalline. So again, we have to classify it according to the Miller index. Yes, please.
Basic doubt, very basic.
Ah.
Actually, I'm a computer science guy, so don't have much of the technical idea about this thing. But as we talked about the nanomaterials, so usually like to give the example of targeted drug delivery and all. So means from application perspective, obviously at a nanoscale also, and that also from material to a particle, some of the properties will change. So if we talk about the targeted drug delivery using the nano IoT method, so in that particular application, if you want to maintain the security, do you have some solutions?
Yes. So basically, in case of the IoT, basically you are using the directly whatever the device we are developing there. So IoT, you are working on the networking part, right? But we are working on with the device development. So directly device would be given to you. So in case of the IoT perspective, how to use it? So you are looking for the security only. I'm not sure about that because mostly whatever the drug delivery system we have developed, that are we are only looking for the whether it is harmful to the human being or not. We are not looking for the security part. So I'm not sure about that.
Sir, all these facilities are available in the United IP or not? Like you have shown the so many facilities there.
Basically, TM is not there, but SEM, sputtering, CVD process about to installation. We will, I think, in the before closing the financial, we will install them. Basically, it was funded by our DST only under the FIST program.
So these all are funded by DST.
Some like I parameter analyze, we got funding through the DST. Some like sputtering and the CVD process we have procured through the institute fund.
So is there any process to access those certain facility out of the?
Yes, definitely. Basically, I think you are familiar with the STM portal is there. That is, I think, maintained by the government of India only. So once it is installed there, we will upload there. So directly you can approach through that and you can access that. Yes. Thank you, all of you.
Thank you, sir. Thank you for providing valuable insights on this topic. Your deep knowledge and engaging delivery have broadened our understanding in this field. On behalf of IIT NAIR Raipur, I express our gratitude and look forward for your such more enlightening interactions in the future. I now invite Dr. Deepika Gupta to honor our speaker with Certificate of Appreciation and badge. Everybody may proceed for lunch. Lunch will start by 1 p.m. and we will meet again in this room at 2 p.m. Thank you.
One small instruction for participants. Those who have not submitted the ID card Xerox, please get it done and submit to us at the earliest. Stream of this side.
लाइब्रेरी में फोन आपका एक दीजिएगा ना, एक बार रिकॉर्डिंग का कैसा हुआ क्या हुआ